This session on cranes will examine some common types, explain the proper setup of a mobile hydraulic unit, and review some revealing accident case histories. The carrier-mounted telescoping boom consists of a hydraulically controlled upper works, mounted on a chassis designed specifically for this type of crane. The boom consists of a heel or base and telescoping sections. Boom angle is changed by boom hoist cylinders or lift cylinders. This type of crane is sometimes used with a jib to increase the operating height. The main hoist line and main hook may be left on the main boom or run over the jib. If two hoisting lines are required, an auxiliary or whip line is used on the jib. Each hoisting line has its own hydraulically powered drum situated at the base of the boom. The outrigger consists of three components: the beam, which is retracted during transport of the crane; the jack, which is used to level the machine and raise the tires off the ground; and the pad or float, which distributes the weight to the blocking, which in turn distributes it to the ground. The carrier-mounted telescoping boom crane is probably the most common mobile crane found on construction sites. It is a very versatile machine and can be easily moved from site to site under its own power. Setup can be performed quickly by one or two men. However, it is difficult for this machine to travel over soft terrain. The carrier-mounted lattice boom crane, sometimes called a conventional crane, is mounted on a specially designed truck chassis. The boom is supported by boom pendants and a live mast. Boom angle is controlled by the boom hoist reeving. Like the telescoping boom crane, the lattice boom crane can be outfitted with two hoist lines, one for heavy lifts and the other for light-duty work. The carrier-mounted lattice boom crane can lift loads to greater heights than the telescoping boom crane, since the boom is considerably lighter. This type of machine is also less expensive. However, assembling or dismantling the boom requires considerable space, time, and labor. The upper works of the crawler-mounted lattice boom crane are identical to its carrier-mounted counterpart. Crawler-mounted cranes can maneuver in close quarters and turn on the spot. They can also travel over rough, broken ground and up grades more easily than truck-mounted cranes. These cranes must be set up on level ground since they cannot level themselves. There are two basic types of rough terrain cranes: the fixed cab type, in which the boom rotates independently of the cab, and the rotating type, in which the cab rotates with the boom. Both types have telescoping booms that can be fitted with jibs or boom extensions. They also have large tires to provide better flotation on soft ground, and outriggers to give the crane more stability for stationary lifts. The rough terrain crane is well suited for traveling with a load, although the load must be over the front, and capacity is governed by travel speed. The crane is very maneuverable and can travel on highways as well as rough ground. The boom crane should be level when lifting or traveling with loads. The telescoping boom truck is mounted on a standard truck chassis that has been specially reinforced. The telescoping boom rotates on the turret or pedestal. The boom angle is controlled by the boom elevating or lift cylinders. This type of boom truck can be equipped with 2 or 4 stabilizers, which take some of the weight off the tires and suspension during lifts. The telescoping boom truck can transport loads as well as hoist them. Lifting capacity and reach are considerably less than those of other carrier-mounted cranes, but versatility makes these trucks extremely useful, especially for light construction projects and equipment suppliers. The boom is mounted on a commercial truck chassis. The knuckle boom articulates or folds under hydraulic pressure and may be equipped with a power drum. This type of truck is most often equipped with front stabilizers only. The knuckle boom truck can be used with a hook or with forks for lifting pallets of material. It can transport as well as hoist materials, but boom configuration limits the reach to a small area surrounding the truck bed. Knuckle boom trucks are very popular with building material suppliers. Probably the most common type of tower crane is the fixed tower with saddle jib. This type of crane has a slewing ring at or near the top of the tower, and the saddle jib swings about the vertical axis of the fixed tower. Saddle jibs are supported by pendants, and the load hook is suspended from a trolley that moves along the jib to change hook radius. The tower configuration can be used to good advantage because it occupies a very limited area. Tower cranes can be set at varying heights up to their maximum freestanding height and can be extended beyond their height limit by tying the crane back to the structure. The climbing tower crane is generally used to good advantage when the building structure is high, the side area is limited, and the structure itself is capable of supporting the crane. The crane is attached to the structure by support frames and wedges. As construction progresses, the height of the crane can be raised by attaching climbing ladders to the frames. The crane is usually mounted on a fixed base at first and later transferred to climbing frames and ladders. Another common tower and jib combination is the luffing jib mounted on a slewing tower. The luffing jib is pivoted at the jib foot and supported by luffing cables. The hoist rope usually passes over a sheave at the jib head, and hook radius is changed by adjusting jib angle. The tower rotates on the slewing ring situated at its base. This allows the operator to face the load at all times. The cab is situated at the base of the tower or at the foot of the jib. Some cranes can be operated from either position. For a given height of tower, a greater height of lift is available with the luffing jib than with the saddle jib. This extra height enables the luffing jib to clear objects that would obstruct a saddle jib. The mobile base consists of either crawler, truck, or trailer-mounted units. Towers on the crawler and truck-mounted cranes rotate with the upper works of the machine. Trailer-mounted towers usually have a slewing ring at or near the top. These units are most often fitted with luffing jibs. Many crane accidents are the result of improper setup. Often, sufficient time is not taken to ensure that all components of the crane are in good working order and properly set up. The operator has to size up the operating area. He must be aware of overhead or underground power lines, live electrical equipment, ground conditions, available space for maneuvering and operating his machine, weight of load, maximum lift height and radius, crane capacity under given conditions, and any other factors influencing the safety and efficiency of the lift. With this information, the operator can decide where to position his crane. The operator positions his crane with the help of a signalman, who remains in clear view of the operator at all times. Once the crane is in place, the operator gets out and surveys the area around the machine to check the ground and the proximity of other equipment or structures. Setup should never be rushed. The costs of an accident far outweigh any savings gained by taking shortcuts. All outriggers must be fully extended for rated capacity. Since much of the weight of the crane and load can be transmitted to only one outrigger, the ground-bearing pressure can be very high. The soft ground on most construction sites cannot withstand the pressure. To prevent sinking or deflection, always use blocking under the outrigger floats to distribute loads over as large an area as possible, preferably 2 to 3 times the area of the float pad. On highly compacted surfaces, however, less blocking area is acceptable. On uneven terrain, blocking can provide the extra height necessary to ensure that all tires are raised off the ground. Once the outrigger beams are fully extended and the jacks are lowered with the blocking in place, the operator can level the machine. Here, the operator uses a leveling bubble inside the cab and makes the appropriate adjustments. Degree of level is a critical factor in determining crane capacity. Before extending the boom, the operator swings the machine to double-check the soundness of outriggers, blocking, and ground, as well as clearance from any structures or equipment. He also watches the leveling bubble to ensure that no settlement has occurred under the outriggers. Hoist rope strength is not usually calculated in the load chart. Before any lift is made, the operator must therefore ensure not only that the crane has sufficient net capacity to lift the load, but also that it is rigged with enough parts of line to lift the load without breaking the hoist rope. Here, the operator is doubling the line before the lift. This reduces tension in the hoisting rope to slightly more than half of what it would be for a single part line. We'll conclude this session by looking at some case histories of crane accidents as well as some examples of safe, efficient operation. The damaged jack resulted from improper setup. Although the beam was extended fully, the jacks were not raised enough to lift the tires off the ground. As the load was being hoisted, the operator lost control. Although he caught the load before it hit the ground, the resulting shock bounced the suspension and tires sideways. The load fell apart, killing 2 workers. The crane on the left is about to lift precast deck sections using a homemade boom of insufficient length. As the boom was lowered, the lower cords contacted the roof, bending the boom and causing its subsequent collapse. To the right, we can see an entrance often used by workers. They were in the habit of looking up for materials being hoisted, but would readily pass under an extended boom. Had anyone been walking under the boom at the time of the collapse, he would almost certainly have been killed. Here we see that the force of impact was sufficient to impale the solid aluminum plate at the boom tip of a piece of reinforcing steel. Here we see the consequences of lifting over the side of a crawler crane. In this case, the upset may not have occurred if the tracks had been oriented so that the lift was over the front of the machine. This accident resulted in a fatality. This incident was the result of setting up on an uncompacted access ramp. When the crane began the lift, ground pressure under the inside outriggers was great enough to collapse the slope and tip the crane over the side. This is a 300-ton mobile crane with a 310-foot lattice boom that was blown over backwards by a gust of wind. Gusts of wind were measured at 95 kilometers an hour at roof level on that day. This accident occurred during a dragline operation while the operator was outside the machine. The operator stepped outside to get his lunchbox while the machine was retrieving the dragline. The bucket caught on a rock in the riverbed and pulled the crane over. This crane was pulling caisson when it suddenly came free, causing the boom to topple over the machine. When working around cranes, always beware of the possibility of boom back. This slide shows the common but unsafe practice of building a form on the rear of a machine and filling it with concrete to provide extra counterweight. Never forget that stability alone does not dictate capacity. There are also limits to the loads that can be applied to the boom, hoisting line, and machine. In many cases, structural capacity may be exceeded before the crane ever tips. A cooling unit is about to be hoisted onto the roof of a building. The unit was relocated twice before the operator could land it. He lifted the load from the street, tried to swing it into place, then had to try again after he had repositioned the crane. Here the jib is used to provide the proper lift angle over the parapet of the building. The boom is actually contacting the building as the load is landed. This hazard could have been avoided if the boom was longer by about 20 feet. This is the load chart used by an operator to determine crane capacity for a given lift. Parameters include length of boom and boom angle, which determine the operating radius, quadrant, and weight of load including rigging equipment. Remember that capacities listed on the chart apply only when the machine is dead level. If the machine is out of level by only 3 degrees, chart capacities may be reduced as much as 50%. This slide shows the load line in close proximity to overhead power lines. There is an area surrounding every live power line that is referred to as the absolute limit of approach. It is strictly forbidden to move any crane boom, load line, or load into this area unless the line has been de-energized. The absolute limit of approach is 10 feet for a line voltage of up to 125,000 volts, 15 feet for a line voltage between 125,000 and 250,000 volts, and 25 feet for a line voltage of over 250,000 volts. In this session, we have examined some of the more common types of cranes found on construction. You should now be more aware of their characteristics and of correct procedures for setting up a mobile hydraulic crane. If you have any questions or wish additional information, please ask your instructor at this time. Reference material is available from your Construction Safety Association of Ontario.